In this video, we are going to demonstrate how to operate our force-sense biopsy robot in different modes and showcase the feedback sent to the input method. After starting our program, we have few options. The first three are used for setup and registration process, where the fourth and fifth are the important options. Starting with the stepwise feedback mode, first we have to give the program the voxel space of the target we're trying to reach for a biopsy. This can be identified by an X-ray or an MRI machine. Then we can use the redundant joint at the base to move the robot in and out of the organ. To realize the full potential of our program, let us first look at the impedance biopsy mode.
Using the Cartesian impedance control example, we were able to modify it so that it is able to track the angle of joint 1 and read any changes made to it. The change is then scaled to a suitable amount that avoids errors and applies it to the position of the z-axis, causing the robot to go either up or down. While the impedance control mode produces a smooth motion, one drawback we have noticed is that there is still a margin of error in accuracy. That is introduced when the robot's end effector is moved, and this makes it impractical for a biopsy as we want accuracy.
To avoid the inaccuracies that are produced by the impedance control, we had to realize another method, and that's where we landed with the stepwise control. Our new method reads the torque that is applied into the redundant joint at the base of the robot, and if the torque exceeds a threshold, we will then move the end effector in and out of the organ. The biggest feature of our program is that we have a feedback applied to the input joint as the user is moving the robot. The way that we identify contact is that the robot can sense torque applied to the end effector, and when the torque is above a threshold, that's when we realize contact was made with an object. After we identify the contact, the robot requires more force by the user to move the end effector, and it will move at a much lower distance for precision. A robot only needs 6 joints to move the end effector into any transformation matrix in the task space. Keeping that in mind, we have demonstrated how our program takes advantage of the redundant joint as a feedback input method of its end effector. With that, we would like to thank you for listening.